All right. Hello, everyone. Who do we have in chat today? Can people in chat hear music? Maybe it was too quiet? Hmm. Apparently there's no music. Okay. Let's see if we go to our broadcast. Can people in chat now hear the music? The background music? Everything in OBS is telling me there's background music. All right, I'll try something else. Oh, okay. Julian is saying there is... Hello, Julian. Welcome back. Thanks for joining again. Oh, okay, so there is some quiet background music, so I'll just turn that up a bit, I guess. Oops. How's that? Is that better? All right. Let me know if the music is not loud enough or if it's too loud or something. Just a little lo-fi background music. It's not loud. Okay, I'll turn it up a little bit more. All right. Hopefully that's good enough. Let me know if you want me to adjust the sound any time throughout this. All right. So just gonna set up a guest browser real quick, and then we can get started. How's everyone doing? Having a good end of your work week or just starting your Friday? How's everyone? End of the work week, very nice. Well, thanks for tuning in at the end of your work week. What takes you here, Nikhil? All right. Well, welcome everyone. Thanks for joining for yet another episode of Let's Profile. Today we're going to be looking at Containerd. In case you're not familiar, Containerd is possibly the most widely deployed container runtime. So if you're using Kubernetes, it's very, very likely that you're using this piece of software. And so I felt like it might be interesting, since we're also running it in our production Kubernetes clusters. And it's one of those workloads that runs on every single machine. I felt like it would be cool if we can optimize some code paths in Containerd, because that would hopefully result in many CPU cycles saved on the planet, which means, you know, less energy used, less you know, ultimately hopefully good for the environment, good for the planet, and just, you know, having some fun on this stream. Hopefully we'll actually find something. I don't know. We do very little preparation for this stream. Maybe that'll change as we go along with the stream, but I think it's a fun kind of setting where we just, you know, as if I was in my regular work day, just trying to do my job as a software engineer, and hopefully we can find something. Nikhil is saying, wanted to check it out. This is the first time I'm attending and wanted to learn or take away something from this session. Awesome. Well, thanks for joining. Super happy to have you. Hopefully we can learn something together. Hello, Samara. Welcome back. All right, let's switch over. So I've already pulled up some production CPU data, kind of similar to the last couple of times. What we're seeing here is one of our production clusters of Polar Signals. And what we're seeing is we're profiling absolutely everything in this cluster using the Parka project. And essentially, you know, I could be showing you the open source project as well. We just happen to run Polar Signals Cloud, which is essentially a hosted version of Parka. So it's very convenient for me to use. But essentially, all the functionality that you're seeing here, you can, of course, you can get in Polar Signals Cloud, but you can also get in the open source version. And today, since we're going to be looking at Containerd, or kind of the shim between Kubernetes and Containerd, called Containerd shim. All of these could be interesting. I don't know. We'll figure it out together, I guess. So yeah, what we're gonna start out with is, since we're not really interested in any of the other workloads, we specifically want to figure out if there's something in Containerd for us to improve. So let's filter right away down to, well, let's start with Containerd shim and see what we can find here. As we can see, there are quite a few data points up here, but ultimately it's not huge what it's using. But again, it's one of those things that runs on all the machines. So if we can find something here in cumulative, this could be a huge saving. So we can see across the last 15 minutes, we have about 1.2 thousand samples. And looking at this right away, something that jumps out is this pretty large frame for background scavenging. So what this essentially means, Containerd is written in Go, and this is effectively garbage collection running here. And there are actually a couple more things. All of these things over here are all related to runtime and garbage collection. This is interesting because this gives me a hint immediately that there's probably something fairly low-hanging that we are going to be able to optimize. Because what this means is that containerd must be generating a bunch of, like allocating a bunch of memory all the time, and then freeing it pretty quickly as well. Otherwise, garbage collection wouldn't be doing this much work. So that's a good sign. That means we should probably be able to fix something by removing some allocations. So that's good. Maybe let's kind of go and dive a little bit into it. So what do we have here? And something that we already saw on the previous streams, which I think is what a really cool thing about continuous profiling data, or generally profiling data. It's a really cool way to see what code is regularly exercised, so we can kind of understand what is this workload doing, right? So containerd specifically is a container runtime, right? Specifically, containerd, container daemon. It kind of takes care of all the things that it takes to run containers. And it looks like, from what we're seeing here, it's running something called stat. I guess this is maybe a long-running Go routine of some sort. And then it's running a couple of controllers, is what this looks like to me. BLK-IO controller, CPU controller, CPU accounting controller, huge TLB controller, and memory controller. Out of all of these, the memory controller appears to be doing the most work. So let's look at this one first. So what do we have here? And feel free to ask any questions in chat should you have any. More than happy to explain anything else that you may be wondering about, or if there's a code path that you're seeing that you think would be cool to check out, let me know. But first thing that kind of jumps out here is the read-uint code path. So we can see even just within the memory controller, this uses almost 12% of CPU cycles in containerd. So that's interesting, and it looks like all it's basically doing is reading files all the time. So that's definitely something that we know very well how to optimize. Let's see if there's anything else here. Growth slice, yeah, that means that we're growing as we're reading files. We kind of keep growing the buffers so that we can fill the buffers with all the data that we're reading from a file. So this makes sense. New object, yeah, allocations like we were thinking. Maybe we can generally have a quick look at, where do allocations within this workload actually happen. So the way that we can find this in Go is using the runtime.new new object function. So we can filter all of these stacks down to all the stacks that include runtime.new object. So we can already see that this is definitely happening a lot in this. This kind of jumps out immediately again. We can continue to see the read-uint code path here, so that's interesting. That's kind of reconfirming that what we were looking at before is probably going to make sense. So new object is always a good one. And then another one that's interesting is, I want to say it's called runtime.makeslice, especially if we're reading files. The biggest thing that we're going to be doing a lot here is going to be creating new slices. Yeah, so it seems like all right, that was it seems like we truly keep allocating new slices and then throwing them away, and then letting the garbage collector find it and free it. And it feels like, if we did a little bit of memory buffering, probably a lot of this can be saved. just kind of scavenging some more, but it looks like everything's kind of pretty similar. So here there's some scanning going on. That's different. So that probably happens after we've read all this data from disk. Maybe another one to look into if we're not successful initially, but it all to me points to, you know, figuring out how we could do some memory buffering in this read-uint code path. So let's have a look at this code. GitHub. And this package is called. It's not the main package apparently, so it's the C groups repository. Okay. Look at this. Let's look at this path here. So it looks like utils.go, and this is version 169. Oh wow, that appears to be pretty outdated. But that's all right. Let's see, utils, read unit. Okay, so this does not look like it's still here. Okay, it looks like this just moved to C group 1 package. And let's see whether the read uint still does the same thing. Yeah, it looks like, I mean, it looks like it's now using not the IOUtil package, but the OS package, which we can have a quick look at, but if I remember correctly, I believe it does do the same thing, where it kind of reads everything, the whole file, and you know, as we can see, there's nothing that we're passing in here. It must be allocating. We can check that out, but I'm pretty confident with that. Once again, if you have any questions in chat, let me know, and I can try to do my best to answer any of your questions. So, was it read file? Hello, hello. Welcome. Fahrstuhlatmosphäre. In case people didn't understand, I think that was a comment on the smooth lo-fi background music being elevator music, I guess is the English term. Welcome, Erkan. Awesome to have you. Hope you're having a good Friday. So yeah, looks like the read file function is opening the file as we expected. It checks and figures out the size of the file. That's interesting. So that it can immediately allocate the right size of this buffer. So that's definitely good for the purpose within the scope of this file, but I think we can do better. What it looks like is that it's basically just reading in chunk, perhaps even, let's see. Yeah, it's kind of trying to read as much data as it can, and just loops over that. So I feel like if we replace this with a function that was reusing a buffer like this, I think we should be able to save a ton of allocations with this. And let's see, and this also means that we will be able to see the runtime.make_slice very, very obviously. And that is exactly what we're seeing here. It appears that okay, because it's now using the OS file, it may be slightly different, but the kind of pattern should still be very similar. All right, well then, let's clone this thing and try to make that improvement. I hope this is big enough for people to see. Let me know in chat if I should make it any larger. But so now C group 1. Let's check out, what was it? Utils.go. And it was the read uint. And it just takes a path and reads that file. All right. So, just like always, in case you're new to the stream, what we're gonna start with is we're gonna write a micro benchmark for this function, so that we can then compare that to our optimized version. So we're gonna first write a benchmark to kind of profile the current state. Then we're going to do our improvement, and then we're going to profile again to see what kind of improvement we've achieved. But actually, before we do that, let's have another quick let's read through what this function actually does. And in chat, we've got a question: do you use LSP and NeoVim? Yes, that's exactly what I do. I use the GoVim plugins, and amongst other things, I also use the Go LSP. That's right. Thank you, Nikhil. Let me know if I can go into any other detail. So, parse. Basically, what we're doing is we're reading this file, and then we're converting this to a string and trimming space. All of these things cause allocations, by the way. So since this is something that appears to be done a lot within the containerd process, so if we kind of go back here and remove any filter, refresh the data to get the most recent data. As we can see, this appears to be done quite a lot throughout the entire lifetime of this process, right? So we may even want to look at that at a later point, but at this point, it's very, very clear that reading the file is definitely the most expensive thing. But we still want to know what exactly it does, so that we can make sure that after we modify this, it still works. So hopefully there are also some unit tests for this, and hopefully reading through this will also get an idea of the nature of what we're reading from this file, right? Obviously, it's saying that we're reading some sort of unsigned 8-bit integer. We can see that from the return type here, uint64. And we're doing that by reading everything from the file, trimming all the spaces, and then trying to parse this unsigned integer. So we are doing that here. So it seems to me that this is truly just a decimal, you know, like base 10 integer that's in a file that's just raw like that there. Maybe we can have a quick look at where the memory controller reads that from. Just to get a good idea of what it is that's being done here. All right, so memory.limit in bytes. All right, that's okay. I see now what this controller actually does. So this is pretty interesting. This means that containerd is constantly probably reconciles the limit that the container has in terms of memory. So that's how I'm reading this function, right? The update function. So we've got a container, and what it's doing is it's reading what the current memory limit is, and then it decides whether it needs to do something, and then ultimately sets the new limit. So that's interesting. So that means, you know, we can just take some number, let's say, I don't know, 3 gigabytes or something in bytes, and we can use that as our baseline benchmark. Maybe we can even use a totally random number. I think that would actually be pretty cool. Let's see, are there tests for the utils? You can see test util test. There's something in here. Read uint. It looks like we don't even have functional unit tests for this. I'm sure that it's still very heavily exercised in all the very specific memory and all the other controllers. So in that case, I think we can get away with just writing a benchmark. All right, so let's write a benchmark. So benchmark read uint. All right, we want to report allocations. That's right, and like that, what's GitHub Copilot generated here for me. We could check at least that we've got no errors here. Although I suppose, just so we'll be sure that we don't have any problems here. This should be comparatively very, very cheap to do. So read uint, and then we can generate a random number, and we just make this very large. All right, thank you, Google. So what do we have here? So that's 92 megabytes. Let's increase that a little bit. Oops. All right. Too much apparently. So now, okay, now we've got like about a gigabyte. So that sounds about right as a representative number to parse. So we'll create a test data directory. And add a uint to this. And I think we already have our benchmark. This should be sufficient already, right? That's surprisingly simple of a benchmark. So we'll do our good old trick of ignoring all tests. That's by writing this regex that ignores anything but an empty string, and your tests can be named an empty string. So that's the good old trick in Go. This is gonna be maybe more difficult to do. What's happening here is I'm on a Mac, and this appears to have a dependency on Linux, which makes perfect sense given that it's working with Linux containers. Let's see, what could we do about that? Maybe just while we're developing this, we can move everything to a separate directory. Not a huge fan of naming things utils, but it'll do for now. And we need our test as well. Let's see, can we now? So what else is in this file? Let's see. Okay, maybe we're gonna need to. Maybe we are going to need to kind of separate this out. I think that's all right. Well, basically, what I'm saying is let's remove everything except for read UN. We'll remove everything about that. All the details. And then, does this call out anything else other than standard lib? String conversion package. It looks like that's it, so let's remove that, and then let's try that one more time. Package utils. Ah, we've got package name mismatches. Test data units of form that was a typo. Our GitHub Copilot generated something and I wanted to name it something else. All right, we've got a running benchmark. Let me just make sure to reset this util set go in this directory, and then we can continue over here. All right, so we've got our baseline. Let's write that. Let's run that a couple of times so we have some statistical significance, and we can save that benchmarking result into our text file. So we can see we've got 5 allocations, about 8,000 nanoseconds, and we can do about we're doing about 140 to 150,000 iterations to gain some statistical significance about all of this. And we're doing 840 bytes. That's allocations in terms of bytes per operation. All right. So how do we improve that? Let's go back one more time and output a CPU profile for this, and it'll be hopefully painfully obvious where we're doing this. Actually, I was talking about the allocations, so let's look at a memory profile. Mem profile and the proc. right, so then we're gonna upload this so that we can look at it in the browser, and we can see really pretty much everything is spent in read file, open. So these are the allocations. Unfortunately, this feature that I want is not implemented in pprofme yet. So I'm gonna pull this up and hello, Matthias. Thanks for joining. So we can see all the allocations are happening down here in new file, byte slice from string. Oops, not this symbol. Let's look at the source. Review it. Everything happens in read file, so let's look at read file. All right, we can see that a pretty significant portion happens in open, so that's also good to know. Another good portion is spent in stat, also interesting. And then ultimately the big allocation is happening in this byte slice. Hey, yeah, Matthias. Yeah, so maybe recapping, what we found is there's this function in containerd, that is used a lot, and essentially what's happening is containerd keeps kind of reconciling that the memory limit, the CPU limit, and so on are essentially the value that we expect it to be. At least that's how I'm reading the code. I could be wrong, and then kind of changing it to the value that it expects it to be. So it keeps reading this value from the C group file system, and then tries to reconcile it kind of with the state of the world that it wants. And it appears that this reading of this file is leaving some allocations left unoptimized, which is kind of unsurprising. We see this rather often because this type of profiling is really not done very widely. Most of the time people do like one-shot profiling, if at all, and they see maybe a 10-second period of time. So it's not super obvious as it is in this case where we're profiling across a very large amount of time as well as across multiple servers. So it becomes painfully obvious where all the CPU time is being spent. So this is no comment, on the folks working on containerd. They're doing a fantastic job. It's just this is the type of thing that continuous profiling suddenly allows you to do. It's just a matter of having the right kind of data available. So yeah, we did already find something that we think we're going to be able to optimize. Well, that is yet to be proven, but I feel pretty good that we're going to be able to do this. So the first thing that I think I would like to try is, instead of always calling this read file function, I would like us to try kind of reusing objects. So we use a buffer here, so that would be I guess it can really just be a bytes buffer, and then what do? We do OS open, and then we defer closing this. Thank you for GitHub Copilot. And then we copy. No, I believe it's IO copy buff. Yeah, maybe we should make this a pointer directory. Oops, that was not my intention. All right, Matthias, enjoy your food. Let's have a quick look at this function signature. I always forget what this looks like. So the destination, that's correct. We want to write into the buffer from our source, which is our file. Maybe we can rename this for clarity. And it returns the number of bytes written, as well as an error. Well, we don't really care about the bytes written. Oh, and we already have an error. Oops, my screen is about to turn off. We return the error in that case. And now we can do exactly the same thing, but we take the buffer, and I believe it's the bytes function that returns the raw underlying byte buffer. That's right. Oh, what was there? It's the string function. I think I prefer the ability to control these allocations here. So, what does it say? Before a new line in argument. I'm probably missing a closing bracket. I think like this. No. Here. Right. So now what we're going to need to do though is we're going to need to add a buffer. So let's go ahead and do that. We allocate our buffer once. So bytes.new buffer. And then important thing that we're going to now need to change is we need to reset the buffer every time we use it, and then we can pass that in here, and we can run our benchmark again. So we run our benchmark again with our new, hopefully improved version, and we can compare our old and new. Hopefully we have some statistical significance, and we can already see we have about a 13% improvement, so not too bad. We can see that the allocations definitely went down pretty significantly, but not completely. So we went from 5 allocations to 3 allocations. I'm going to guess that that was probably the majority of our time saved. And something that we're also going to need to note is that now that we introduced this buffer reusing, that also means that we are going to need to have some like byte buffer pooling in order to be able to actually reuse this stuff throughout. But maybe, I don't know, maybe the controllers themselves are not running concurrently or something, and that would mean that we can actually reuse a single buffer all the time. That would be pretty exciting, but that's for later, I would say. So let's have another look at some profiling data of this. So maybe we can do count 5 and then view profile. Let me know if you have any questions in chat, but something that we can already, like, even, you know, just from memory, we can see that we definitely went down from about 8,000 to about 7,000 nanoseconds per operation, and we're doing significantly more cycles. We can see three allocations consistently. So that's already a good start, but let's see where we're still spending our time. So we can see our read uint function The IO copy, yeah, I guess that makes sense. It's primarily, it looks like we're almost entirely waiting only to fill the buffers. So this doesn't strike me as something that we're going to be able to get rid of. Close, okay. Yeah, that's also going to be hard to get rid of. But here, what's this? OS open file. Probably not something we can do either. It ultimately just ends up doing syscall. Yeah, it looks like there's really not much more that we can do here. But let's do the calculation, right? Like if we, what did we say? Our benchmark improves by 13%. If we took our read uint function that represents about 200 samples out of how many? Out of 971. 200 divided by, I mean, this is about 20%, right? A little bit more. And if we take 13% of that, that means we've got about a total saving of 3%, 2.5%. That's not too bad for, you know, we've been at it for about half an hour. So I'm pretty happy with that already. So let's continue down this path, I would say. Let's start to make use of this new and improved function. Maybe what we can do is expose this function now. Say read uint, read a uint64 from the given file, and then to reuse and uses the given buffer as branch base. The buffer is intended to be reused across parts. What I find interesting is that we didn't see. Did we see allocations for parse uint? CPU milliseconds. I guess in terms of the time spent in this, it's very, very minimal, but it might still be worth looking at a memory profile. Rename the function. So we gotta recreate it as well. Any questions on chat? Any comments? Anything I can clarify? Looks like we're still, I mean, we didn't make any changes, so that we have 3 allocations makes sense. Oops, I'm doing the same profile. So looks like new file performs an allocation, which probably makes, no, it performs multiple allocations. So this might be yet another example where we might want to look at the source int. Yeah. Right. And then OS open. Byte pointer from string. All right, there may actually, because this is also Darwin specific, there may be less allocations on Linux. I don't know for sure. I'll be honest. Maybe it's even bigger. I don't know. Let's see if we can find something. File. What was the? What were we just looking at? Oops. Open. It's os file.go. Yeah, no, this. Oh no, it was up here. This one. That's the one I'm interested in. Source. Syscall. Yeah, okay, this definitely is operating system specific. So let's have a quick look at the syscall package. And we open functions. Right, and it depends on, let's say it's Linux AMD 64, and we want to see, okay, maybe it is just called Linux, okay, open at, where's lowercase open at? Looks like it's probably going to have the same allocation now. But let's just figure that out once and for all. Looks like there's a Unix version of it, and that does that, and that. Yeah, this is also going to be an allocation. So, but what I'm seeing here is a single allocation, whereas here it appears to have been multiple allocations, or maybe this is just a bigger allocation. This is objects total, bytes. Yeah, it could just be, I don't know, over here. This is the one. Objects. Hard to say. It depends on how many iterations are happening here. All right. Enough. Looked at this. All right. So. Let's see how we can integrate it. We already ideally we just remove this and then we can go through each of these. Seems like we're gonna need to be able to be successful with this. I feel like we need to continue on a Linux machine, which I don't have handy right now for the stream. So let's maybe just have a quick look at the amount of times that we're calling this function, reviewing. Okay, it's not really all that often. Truly only in the places that we've seen profiling data for. Nikhil is asking, can we clone the project in Gitpod and assume they are Linux? Not sure if it'll help. We can give that a try. I don't even think I have a Gitpod account. Alrighty. Great idea, thank you, Nikhil. We'll do the system. Can you open? I didn't think so. Alright, I guess we'll use... I am not a Visual Studio Code user, so this is going to be interesting. I work in software engineering. I'm exploring... Where is the... I'm exploring Gitpod on the screen. For personal projects or open source, I guess. Remote... Aha, yeah, this is kind of what we're doing. I'm signing up for other. Hoping this is backed by a Linux machine, since I want to write something Linux specific. No workspaces. All right. Nikhil, I think you're gonna need to help me. Okay. Maybe I can figure this out. Container D groups. Just create workspace giving the GitHub project name. I feel like that's what I just did. GitHub.com/containerd/. Do I maybe need to fork it first for this to be possible? Okay. That makes sense. Do that. Alright, let's give that another try now. We will need to reload this. All right. I think we're getting there. Thanks for the suggestion, Nikhil. You're gonna watch me using Visual Studio Code for the first time, so this could be interesting. Alright. That looks familiar. Looks like it's a Linux box. don't know, how do we do that? OS release or something? Yeah, looks like this is an Ubuntu. Good. Can we run tests here? Yeah, we can run tests here. Nice. Thank you, Nikhil. Very cool suggestion. Could I turn down the music just a smidge? No problem, Sumera. Let me switch over real quick to this, and then I can turn down the music a bit. How's that, Sumera? Let me know. All right, now we can switch back. Starting to get the hang of this OBS thing. Now, if I can only start streams the way that they're supposed to be started, then I don't need to start a second one. It's the second time now out of 4 streams that has happened. All right. So, we're gonna. I guess then here we could actually replace it directly in the utils. That was just how I usually do things. That's not how it's gonna work here. Whoops. What's here? Do you want to install the recommended extensions for Go? Sure. Would you like to install? Do not synchronize. Hopefully that did the trick. No, where were we? Read you end. Let me copy that. And let me also make this much larger. And close this. The only thing that we changed, so oh my. All right, that worked. No, I don't. And we want our store, create a new file. Here we go. Util. And we're gonna copy our benchmark. Oops. Now we can do the C1 package again. Do that and save. Oh. How does that work? Redo it like that. This should already work. Let's see. How do I get that terminal back? Anybody in chat knows how to use Visual Studio Code and can let me know how I can get that terminal back? Terminal, new terminal. I think we got it. Now we want to do our. Just want to make sure that this stuff still works. Of course, now we're not. Now we're not. Now this doesn't work because we still need to adapt to use a byte buffer everywhere. Oops. So, how do you all use this stuff? I need my Vim concentration mode. This is unusual. How do I talk? Control plus? What is it on a Mac? What's control on a Mac? Oops. All right. We need to find all of our. It's already telling us all the places where it needs to be fixed. That's nice. So I want to know, is this thing called concurrently or just once? Where can I search through this project? Control Shift F. Is it maybe? Aha. Yeah, it's on the Mac. It's the Command Shift F. Thank you very much, Nikhil. So, where is this called? And then it's called in defaults. And where is default? Manager. Yeah, that's system slice. Defaults here. Defaults. Default. Okay. Where is that called? Alright, I mean, this all strikes me as that this is all one Go routine that's doing all of this work. So that should mean it should be very, very safe for us. Whoops. Let's search for the, what was it? It should be very safe for us to just have a buffer in each of these, so that we're reusing. So that, and then new buffer, and that needs a nil here, and then for this we pass speed.buff, and it looks like we just need to save and it adds it. Yeah, that's looking good. And we just do the same thing in all of them. Buff, bytes buffer, buff is bytes buffer, nil. And where is redo end? Here we go. And we add controller is off buff. Font controller. It's H. Right. Okay. Yep, that worked. So we'll do, since we're already here, we'll do m.buff, even though this doesn't exist yet. It looks like we have a second occurrence. So we'll do m.buff as well. And we'll do the memory controller buffer, buffer. And where's this thing being instantiated? Here we go. Buff is find stuff in buffer. Nil. In case you're wondering, this nil argument is you can pass in if you want to initialize the buffer initially. We could do that. We could pre-allocate like 128 bytes or something like that. We probably don't need more than that. Since we're reading integers that are in base 10, and yeah, more than 128 characters is probably very, very unrealistic. So we could probably pre-allocate these so that we never have to grow, and that means that we have a contiguous slice of memory. That might actually be nice. So let's do that. Be nice. Sure, and then I think 64 seems like quite a lot already. Even 32. Yeah, even 32 should be plenty. 16 might be not enough, but I think 32 should be plenty. And I always forget, does it need to be, do we only need to allocate capacity or size? Let's see. Going bytes. Perfect. It's intended to prepare buffer use to. Okay. We have an example here. If only one parameter mentioned, it takes as both cap size. That's right. Yeah, if the make that we did here, that means that the slice is already of length 32 and capacity 32. What I'm trying to figure out is whether we should be doing this, in which case we would have the capacity of 32, so we can write things or append things up until 32 bytes, and we wouldn't cost additional allocations. And we will always make sure that 32 bytes are contiguous. But we would say that the length is currently 0. So we should figure out what the buffer wants. That makes sense. Okay. My intuition says it probably has to be this one, because if it wasn't, then it would grow the slice anyway. So I'm guessing that it's gonna look internally whether it needs to grow the slice or not. So I think we can probably leave it at this. And then do the same here. We have 0, 1, 32. All right, and then let's go on to the next one now. This is done. p.buf. Give this a buffer as well. Righty. It looks like we've got all of them, so let's expected PIDs limit. Okay, that's good. We've got all right, maybe let's remove that pre-allocation one more time just to see if it would work without and to see if it's just that or if there's something else that we maybe broke, right? Where are we? What happens in the test? What's this test called? Test def memory controller. Some key bindings don't go to terminal. Okay. Hopefully that works. Back to this. Yes, okay. Yeah. Value at index 11. All right, let's see what this is about. Memory test 149. All right, so we've got a reader. That's this file. So this file actually looks a little bit different than I originally imagined. So we might need to change a couple of things. But we're looking for line number 149. Where we've got a memory controller and we call stat on it. That's what we expect. And then parsing. We're opening this file. What happens next? Can't get stats. Review it. What do we got here? I mean, this looks pretty suspicious if I'm honest. 0 and then a new line and then a 1. That doesn't seem right. Let's close all these other things that we've got open here so we can focus. Can't get that string conversion parse uint. Hard to say now where this happens. Parse that. Whoops. Oh. Accidentally pressed back on my mouse. Where were we? What was the test here? Let's just run all the tests again. Maybe we can use a smaller one. This one seems to be a bit simpler. Test PIDs. How do I get the file tree back here? Ah, here we go. So, test PIDs, create a new mock, which is emptier. We create our defaults. Testing TB. Okay, yeah. It creates a emptier. Looks like we create a couple of files here, and then we have a mock group that we return. Okay, that sounds good. And where do we get our error? On line 86. So the PIDs that we receive are not what we expect. And that's coming from metrics PID current. So I suppose metrics are being set in stat. So this file doesn't looks like it's not what we expect it to be. We do not, what did we say? We need to reset the buffer. So actually let's reset the buffer here and not in our test. We had a test for this. That's safer. That way we can be sure that it truly will always be reset. Now let's see if that, now it passes. So what we were doing was we just kept reading new things into that buffer. And then, you know, we were surprised that we read stuff that we previously read already. So that happens. Now you can see everything that happens on these streams is unplanned. Just normal life of software development. All right. That also means that we can now add back that pre-allocation that we removed because we thought that we may have broken something because of that, but it looked like that was not the case after all. So test this one more time. So yeah, now it looks like we're pretty much done. We proved that we reduced this particular function by 13% roughly, but maybe we had a theory earlier that potentially there's actually more savings on Linux than on Darwin. So let's give that a try, right? So we have our util test. That's muscle memory. Trying to open it in NeoVim. We've got our test benchmark here, so we can do this again, bench, and run our benchmark. Test data unit, no such right. Oh, okay, yeah, that makes sense because we don't have that here. So let's copy that from here, and then create. We did create that, but we didn't actually. We did create the directory, but we didn't actually write anything into it. So we want the UN and then that, and we save that. We can close that again. So now we'll try that again. And it looks like this is actually adding an additional allocation. So that's interesting. But and this could just be that maybe this particular CPU is much faster. It looks like we're doing way more iterations, right? And we're using much less nanoseconds per operation for this. And we're seeing 136 bytes per operation. That's interesting. Let's see what that was on OS X. Did I remove it? Oh no, it's in the util bucket. Huh. So there is an additional allocation here. That's interesting. Where is that happening? This time we're gonna need to use the command line utilities. So let's see. Read uint continues to be the offender. Is course I help. Lines. I don't use this very often. Comments, no, I want to see. Well, I guess can't do that. Then, how are we gonna look at this profiling data? I guess we can't. But we did show that we definitely have only 4 allocations, so we can have a look at what that would be like if we can kind of simulate that. It's not exactly the same thing, but we can still the muscle memory. What if we go in here and moved this buffer allocation in here? this out, and then we run our benchmark. They would count 5. And this is our old. So we're gonna need to reallocate this memory all the time. So that's not, you know, that's what we try to avoid. So if we then compare it to our new, hopefully I saved before. I don't remember if I did. Not. We can always rerun one more time. Hopefully this tool is available. It is not. Bench that. How do we install it? Like this. Yeah, I thought it was like at latest or something like that. Yeah. All right. So that looks like it's more like a 5% improvement. How did the allocations change? We did change from 7 allocations to 4 allocations, so that's pretty similar to what we observed. And instead of about 2 kilobytes allocated, we now allocate about 136 kilobytes. So we removed pretty significantly the amount of bytes that are being allocated here. So that's probably still quite a bit more that we can do with this, but I'm still pretty happy with this result. It's probably, the reality is probably it's somewhere in between 5 and 10%. So that means that we probably have something like a 2% improvement. And we can always, I want to take a quick look at them. These are probably also rather noisy machines. Yeah, we earlier saw that we had something like 3,000 nanoseconds. So I'm not sure in terms of benchmarking how reliable this particular environment is. I mean, for benchmarking, you usually want, you know, a dedicated machine where nothing else is running on it, and this is a very intentionally very multi-tenant environment. So that's okay. That's not what this is made for. All right, I think we're done. I think I'm gonna open the pull request separately. I don't think we need to do that on the stream. Yeah. Any last words from anyone on the chat? I'll switch over to this one. Yeah, I think we had yet another pretty cool stream. Looks like we improved something in the realm of 2% of CPU time within Containerd. That's pretty exciting. You know, this is a piece of software that's run on probably millions, if not tens or hundreds of millions of machines. So saving 2% of CPU time on a workload like this can actually have a pretty significant effect on the planet, right? So I'm excited that we actually managed to find something. Like I said, these are pretty unprepared streams, so there will probably come a time in the future when we will not be able to find anything. So I'm happy while we still continue to find fairly low-hanging fruit, right? Nikhil says, It was a great session and learning on how you dig and did that change. That was crazy. Loved it. Thank you so much, Nikhil. Thanks for stopping by. So yeah, thanks for everyone for stopping by. Everyone else, thanks for everyone who was active in chat. I definitely had yet another good time on this stream, and hopefully see everyone next time. All right. Thanks everyone. Bye bye.